This video is about lemniscates. So we want to graph r squared equals 4 cosine 2 theta, and we're going to do that by graphing y equals 4 cosine 2x on the rectangular coordinate system at the same time as this graph, and we'll see what that looks like. As we see the polar and rectangular forms of y equals 4 cosine 2 theta and r squared equals 4 cosine 2 theta being graphed at the same time, we notice that the polar form appears to have a pause or a break in it. And that pause in the drawing appears to be whenever the rectangular function is under the x-axis. So what we probably noticed was that every time the rectangular graph was underneath the x-axis, our polar graph was not graphing anything. So, as we were graphing this part, we were at 0, 4, which in this lemniscate, or in this polar graph, if I have 0, 4 for x and y, that's going to translate into 2, 0 for r theta. Now, why is it 2? Well, notice that in these problems, we have an r squared. So that means, because we have an r squared, if this y value is 4, then this r squared value would be 4, so r would equal 2. So we're starting at 2. And then what happens is by the time we get to pi fourths, we're at 0. Then there's a pause. We don't actually graph anything again until we get to 3 pi fourths. So at 3 pi fourths, we're at 0. And then by pi, we get all the way up to 4 again, which when we take the square root, we get 2. And then it comes back down. So then at 5 pi fourths, we're back to 0. Then we pause, don't do anything. And then it finishes by graphing over here. Now, all of these are pauses that don't exist in our polar graph, because when we take an r squared equals something, what happens when we have r squared equals a negative value? Well, that is not existent. It only exists in the imaginary numbers, and we're not dealing with that when we graph it. So, what's happening in the rectangular graph when the lemniscate is pausing? There's a negative value, which means r squared cannot equal that value. And since that's the case, we have a pause in the polar graph. So what we may notice about this is that even though there's 2 entire cycles in this rectangular graph, so notice we have 1 cycle, and then a second cycle. Even though there's 2 entire cycles in the rectangular graph, that only does 1 entire period in this r squared equals 4 cosine 2 theta lemniscate. So as a result, the period of a lemniscate is 2 pi. Now, I guess we should formally define what a lemniscate is. A lemniscate is something of the form r squared equals a squared sine or cosine of 2 theta. So this is not just any old n. We need the number 2 to be in there. So this could be a sine or a cosine, but it has to be of this form. So now let's do a couple examples. We'll graph r squared equals 9 sine 2 theta. So what's going to happen is we're going to look at where this rectangular graph is positive, because we can't graph anything that's negative, because r squared can't equal a negative number. So we'll start at 0, and then on this we get at pi over 4, comma 9. Now remember, the y value represents r squared. So if r squared equals 9, that means r equals 3. So by pi fourths, we're at 3, and then by pi halves, we get back down to 0. So it'll look something like this. Then, while we're underneath the axis, we pause. Then 0 comma pi will be the next point on the polar graph. And then the next one we see is at 5 pi fourths, r equals 3, since r squared is 9. So that means we'll be at 3 comma 5 pi fourths. And then by 3 pi halves, we're back to the pole, and then we finish with not drawing anything. So that's kind of what this one would look like. Y equals 16 cosine 2x will match up with r squared equals 16 cosine 2 theta. So again, everything under the axis, we don't draw, because r squared cannot equal a negative number. So we start at 16, which when we take the square root, we end up with r equals 4. So we would end up graphing 4, 0. Then by pi fourths, we're back to 0. We pause until we get to 3 pi fourths. And then until pi, we end up at 4. And then from pi back to 5 pi fourths, we end up back at 0. We pause while it's under the axis. Then from 7 pi fourths to 2 pi, we go from an r of 0 to an r of 4. So we end up at 4 comma 2 pi, which is in the same spot that we started with. So notice that these lemniscates kind of look like infinity signs. Seems like that's a pattern that is developed. We had an infinity sign here, and in these two, it kind of looks like an infinity sign. So let's explain the difference in when we have r squared equals a squared sine 2 theta versus the same thing with a cosine 2 theta. And it appears that when we have the sine 2 theta, the infinity sign appears to be tilted sideways, whereas on some kind of diagonal tilt, and with the cosine, it looks like it's a regular old infinity sign. So this lemniscate here that has the sine is symmetric over the line theta equals pi fourths. You can also say it's symmetric over 3 pi fourths, because if you fold it over this lighter blue line, this bluish gray line, it would still fold on top of itself. For the cosine, we have the polar axis, or theta equals 0, and it's also symmetric over theta equals pi halves. Now let's do two quick graphs where we have a negative up here. So our temptation is to think that because we have r squared equals something with a negative, our temptation is to think that it doesn't work at all. However, it does work, because if we graph these things, we actually have values where the function is positive. So it just changes when we graph stuff. So again, r squared can't equal a negative, but when the function is positive, that means that we're basically taking a negative times a negative, and we end up with a positive. So we start at pi halves, get up to r squared equals 9, so that would end up being at 3 pi fourths. The r value would be 3, so at 3 pi fourths. And then by theta equals pi, we're back to r equals 0. So it would look something like this. And then from 3 pi halves, we're at 0 comma 3 pi halves on the polar plane, and then 3 comma 7 pi fourths, and then back to 0. So what we notice is we have another infinity sign. It's just tilted the other way. So we had one that was in the first and third quadrants of the rectangular coordinate system. Here we have one that's in the second and fourth quadrants. Now let's look at the negative cosine graph that's identical to number 2, except with a negative sign. So all of these parts end up being negative. We're not going to draw those. So 0 comma pi fourths would be our first thing, and it looks like this part didn't copy. So 0, comma pi fourths would be the first, and then it ends up at 16, which is going to be 4. So 4 is up here. We're somehow missing this circle too. And then it comes back down at 3 pi fourths for the theta. We end up at r equals 0. Then we pause from 5 pi fourths, or 0, comma 5 pi fourths, up to 4, comma 3 pi halves. I think I went one too far. 1, imaginary 1, 3, 4. And then back down at 7 pi fourths. So what we notice is a graph that follows this trajectory with a pause anywhere it was negative. So here's some lemniscate properties. The number of loops is 2. The length of each loop is a. Notice it's the square root of this number. If it's a cosine graph, it's symmetric over the polar axis, and theta equals pi halves. If it's a sine graph, it's symmetric over theta equals pi fourths and 3 pi fourths. And which thing it gets drawn over is depending on whether you have a positive or negative in front. So with positives, the graphs look like this for sine and cosine. And with negatives, the graphs look like this.